Karla, what is your opinion about satellite?
Well, basically, a satellite is a physical object that orbits or rotates about some celestial body.
An object that orbits? How?
Satellites are launched and they keep in orbit depending upon a physical and mathematical law called orbital dynamics.
From what I've learned before, if a satellite were launched vertically from the Earth and then released, it would fall back to Earth because of a gravity.
Yes, that's right. For the satellite to go into orbit around the Earth, it must have some forward motion. There are factors affecting the rotation of a satellite in an orbit. First, forward motion produces inertia, which tends to keep the satellite moving in a straight line, and gravity tends to pull the satellite toward the Earth. The inertia of the satellite is equalized by the Earth's gravitational pull, and lastly, the satellite constantly changes its direction from a straight line to a curved line to rotate about the Earth.
The closer the satellite is to Earth, the stronger the effect of the Earth's gravitational pull. So, in low orbits, the satellite must travel faster to avoid falling back to Earth. The lowest practical Earth orbit is approximately 100 miles. At this height, the satellite speed must be about 17,500 miles per hour to keep the satellite in orbit. At this speed, the satellite orbits the Earth in approximately 1.5 hours. Communication satellites are usually much farther from the Earth. A typical distance is 22,300 miles. A satellite may travel only about 6,800 miles per hour to stay in orbit at that distance. At this speed, the satellite rotates about the Earth in approximately 24 hours, the Earth's own rotational time.
There are two types of orbit. First, the circular orbit and the elliptical orbit. As shown in the figure, a satellite rotates about the Earth in either a circular or an elliptical path. Circles and ellipses are geometric figures that can be accurately described mathematically. Because the orbit is either circular or elliptical, it is possible to calculate the position of a satellite at any given time.
In a circular orbit, the height is simply the distance of the satellite from the Earth. However, in geometric calculations, the height is really the distance between the center of the Earth and the satellite. In other words, the distance includes the radius of the Earth, which is generally considered to be about 3,960 miles.
As shown in the figure, when the satellite is in an elliptical orbit, the center of the Earth is one of the focal points of the ellipse. In this case, the distance of the satellite from the Earth varies according to its position. Typically, the 2 points of greatest interest are the highest points above the Earth, the apogee, and the lowest point, the perigee. The apogee and the perigee distances typically are measured from the geocenter of the Earth.
If it rotates, does it have speed?
Yes, as indicated earlier, the speed varies according to the distance of the satellite from the Earth.
For a circular orbit, the speed is constant. But for an elliptical orbit, the speed varies according to the height. Low Earth satellites of about 100 miles in height have a speed in the neighborhood of 17,500 miles per hour. Very high satellites such as communication satellites, which are approximately 22,300 miles out, rotate much more slowly, a typical speed of such a satellite being in the neighborhood of 6,800 miles per hour. How is the rotation of a satellite being measured?
Is measured in terms of period. The period is the time it takes for a satellite to complete one orbit. It is also called the sidereal period. Another method of expressing the time for one orbit is the revolution or synodic period. One revolution is the period of time that elapses between the successive passes of the satellite over a given meridian of Earth longitude.
Do you know that as the satellites rotate, there is an angle formed between the line that passes through the center of the Earth and the North Pole, and the line that passes through the center of the Earth but that is also perpendicular to the orbital plane is called the angle of inclination.
When the angle of inclination is 0 degree, the satellite is directly above the equator. When the angle of inclination is 90 degrees, the satellite passes over both the north and the south poles once for each orbit. Orbits with 0 degree inclination are generally called equatorial orbits, and orbits with inclinations of 90 degrees are referred to as polar orbits.
The angle of elevation of a satellite is the angle that appears between the line from the Earth station's antenna to the satellite and the line between the Earth station's antenna and the Earth's horizon. Also, there is so-called geosynchronous orbit.
And that is
In GEO, the satellite rotates about the Earth in exactly 24 hours. It appears to be fixed or stationary. The antenna is pointed at the satellite and remains in a fixed position, making continuous communication possible. Most communication satellites in use today are of the geosynchronous variety.
how is the position of a satellite be identified?
To use a satellite, you must be able to locate its position in space. That position is usually predetermined by the design of the satellite and is achieved during the initial launch and subsequent position adjustments. Once the position is known, the Earth station antenna can be pointed at the satellite for optimum transmission and reception. After knowing its definition and principle, what are its significance?
One of its use is for communication purposes. What if a transmitting station cannot communicate directly with one or more receiving station?
If a transmitting station cannot communicate directly with one or more receiving stations because of line-of-sight restrictions, a satellite can be used. The transmitting station sends the information of the satellite, which in turn retransmit it to the receiving stations. The satellite in this application is what is generally known as a repeater. These are the frequency bands used in satellite communication. The satellite communication system consists of two basic parts.
The satellite or spacecraft and two or more Earth stations.
The difference between the two is that the satellite performs the function of a radio repeater or relay station, while
the two or more Earth stations may communicate with one another through the satellite rather than directly point to point on the Earth. This is a block diagram of a satellite. All the major subsystems are illustrated. The solar panels supply the electric power for the spacecraft. They drive regulators that distribute the power to all other subsystems. And they charge the batteries that operate the satellite during eclipse periods. And AC to DC converters and DC to AC inverters are used to supply special voltages to some subsystems. Total power capability runs from a few hundred watts in the smaller units to several kilowatts in the largest systems.
there are two basic multi-channel architectures in use in communication satellites. One is broadband system. The broadband system, a typical communication satellite spectrum is 500 MHz wide. This is typically divided into 12 separate channels, each with a bandwidth of 36 MHz. The center frequency spacing between adjacent channels is 40 MHz, thereby providing a 4 MHz spacing between channels to minimize adjacent channel interference.
And the other is a fully channelized system. The channelization process occurs in the remainder of the transponder. The bandpass filters separate out the unwanted mixer output signals and retain only the different signals. Then, individual high-power amplifiers are used to increase the signal level. These are usually traveling wave tubes. The output of each TWT amplifier is again filtered to minimize harmonic and intermodulation distortion problems. These filters are usually part of a larger assembly known as multiplexer or combiner. This is a waveguide cavity resonator assembly that filters and combines all the signals for application to a single antenna.
Today, virtually every satellite uses solar panels for its basic power source. Solar panels are large arrays of photocells connected in various series and parallel circuits to create a powerful source of direct current. Early solar panels could generate hundreds of watts of power. Today, huge solar panels are capable of generating many kilowatts. A key requirement is that the solar panel always be pointed toward the sun.
All satellites have a telemetry command and control subsystems that allows a ground station to monitor and control conditions in the satellite. Telemetry system is used to report the status of the onboard subsystems to the ground station. The telemetry system typically consists of various electronic sensors for measuring temperatures, radiation levels, power supply voltages, and other key operating characteristics. A command and control system permits the ground station to control the satellite. Typically, the satellite contains a command receiver that receives control signals from an Earth station transmitter.
The application subsystem is made of the special components that enable the satellite to fulfill its intended purpose.
For a communication satellite, this subsystem is made up of the transponders.
All Earth stations have a relatively large parabolic dish antenna that is used for sending and receiving signals to and from the satellite. Early satellites had very low power transmitters, and so that the signals received on the Earth were extremely small. Huge high-gain antennas were required to pick up minute signals from the satellite. The Earth station dishes were 80 to 100 feet or more in diameter. Antennas of this size are still used in some satellite systems today, and even larger antennas have been used for deep space probes.
The downlink is the receive subsystem of the Earth station. It usually consists of very low noise preamplifiers that take the small signal received from the satellite and amplify it to a level suitable for further processing. The signal is then demodulated and sent on to other parts of the communication system. In RF tuning, as shown in the figure, the first local oscillator is made adjustable. Typically, a frequency synthesizer is used in this application. The frequency synthesizer generates a highly stable signal at selected frequency increments. The frequency synthesizer is set to a frequency that will select a desired channel. In RF tuning, the second local oscillator has a fixed frequency to achieve the final conversion.
In IF tuning, the first local oscillator is fixed in frequency and the second is made tunable. Again, a frequency synthesizer is normally used for the tunable local oscillator. The receiver ground control equipment, or GCE, consists of one or more racks of equipment used for demodulating and demultiplexing the received signals. The down converters provide initial channelization by transponder, and the demodulators and demultiplexing equipment process the 70 MHz IF signal into the original baseband signals. Other intermediate signals may be developed as required by the application.
The transmit subsystem consists of two basic parts, the up converters and the power amplifiers. The up converters translate the baseband signals modulated onto up carriers to the final uplink microwave frequencies. The power amplifiers generate the high power signals that are applied to the antenna. The modulated carriers are created in the transmit GCE.
The telemetry equipment consists of a receiver and the recorders and indicators that display the telemetry signals. The signal may be received by the main antenna or a separate telemetry antenna. A separate receiver on a frequency different from that of the communication channels is used for telemetry purposes.
In some satellite systems where communication is the main function, some instrumentation may be a part of the ground station. Instrumentation is a general term for all the electronic equipment used to deal with the information transmitted back to the Earth station. The instrumentation subsystem is in effect an extension of the telemetry system.
A very small aperture terminal is a miniature low-cost satellite ground station. In the past, most ground stations were large and expensive. Large because of the huge dish antennas that were often needed, and expensive because of the equipment costs. But over the years, semiconductor and other technology breakthroughs have greatly reduced the size and cost of ground stations. Now, let's talk about the satellite application.
I'll start with communication. The main application for satellites today is in communication. Satellites used for this purpose act as relay stations in the sky. They permit reliable long-distance communication worldwide. They solve many of the growing communication needs of industry and government. Communication applications will continue to dominate this industry.
The second application is the direct broadcast satellite. A more recent satellite TV service is the Direct Broadcast Satellite or DBS that uses special broad US coverage satellites with high power to transmit cable TV-like services direct to homes equipped with the special DBS receivers. The Direct Broadcast Satellite system is an all-digital system. Data compression techniques are used to reduce the data rate in order to produce high-quality picture and sound.
Satellite application today is satellite-based cellular telephone service. Current cellular telephone systems rely on many low-power ground-based cells to act as intermediaries between the standard telephone system and the millions of roving cellular telephones.
The fourth application is the digital satellite radio. One of the most popular options in new cars and trucks is a digital satellite radio. This service provides hundreds of channels of music, news, sports, and talk radio primarily to car portable and home radios. Conventional AM and FM radio stations cover only short distances and are subjected to local and even national radio propagation effects.
Another application of satellite is in surveillance or observation. From their vantage point high in the sky, satellites can look at the Earth and transmit what they see to ground satellites for a wide variety of purposes. For example, military satellites are used to perform reconnaissance. Onboard cameras take photographs that can later be ejected from the satellite and brought back to Earth for recovery. TV cameras can take pictures and send them back to Earth as electric signals. Infrared sensors detect heat sources. Small radars can profile Earth features. Is GPS or Global Positioning System related with satellite navigation systems?
Yes, it is a satellite-based navigation system that can be used by anyone with appropriate receiver to pinpoint her or his location on Earth. The array of a GPS satellites transmits highly accurate, time-coded information that permits a receiver to calculate its exact location in terms of the latitude and longitude on Earth as well as the altitude above sea level.
The fully implemented GPS consists of 24 main operational satellites plus multiple active spare satellites as shown. The satellites are arranged in 6 orbits, each orbit containing 3 or 4 satellites. The orbital planes form a 55 degrees angle with the equator. The satellites orbit at a height of 10,898 nautical miles above the Earth, which is 20,200 kilometers. The orbital period for each satellite is approximately 12 hours.
A GPS receiver is a complex super heterodyne microwave receiver designed to pick up the GPS signals, decode them, and then compute the location of the receiver. The output is usually an LCD display giving latitude, longitude, and altitude information and/or a map of the area. There are many types of GPS receivers. More than 40 manufacturers now make some form of GPS receiver. The larger and more sophisticated units are used in military vehicles.
As shown in the figure, this is a general block diagram of a GPS receiver typical of the simpler, low-cost handheld units on the market. The receiver consists of the antenna, the RF or IF section, the frequency standard clock oscillator, and a frequency synthesizer that provides local oscillator signals as well as clock and timing signals for the rest of the receiver.
And lastly, the Global Positioning System application. The primary application of GPS is military and related navigation. GPS is used by all services for ships, aircraft of all sorts, and ground troops. Civilian uses have also increased dramatically because of the availability of many low-cost portable receivers. In fact, it is now possible to purchase a handheld receiver for less than $200. Most civilians' applications involve navigation, which is usually marine or aviation related. Hikers and campers and other outdoor sports enthusiasts also use GPS.
Commercial applications include surveying, map-making, and construction. Vehicle location is a growing application for trucking and delivery companies, taxi, bus, and train transportation. Police, fire, ambulance, and forest services also use GPS. GPS-based navigation systems are now widely available as accessories in cars to provide a continuous readout of current vehicle location.